Okay, so this deep dive, we're looking at this really interesting paradox with modern AI,
Yeah,
right?
absolutely.
You have these massive, large multimodal models, LMMs, and they are just incredible at, basic
Oh,
recognition.
for sure. But then you ask them to do something that requires some real sophisticated visual reasoning.
Yeah, exactly. Like figuring out how abstract shapes might fit together, or finding a really subtle similarity between two complex images.
And they hit a wall.
So what's the hang up? Why do they struggle so much with that?
Well, the source material points to something that calls a language bias.
A language bias.
Yeah. Most of these models, they use what's called a LLIA style architecture. And what that means is the visual input it gets sort of flattened into the text space almost immediately.
So it has to talk about the image before it can actually think about it.
You've got it. It has to translate this incredibly rich visual world into language first. And, well, a lot gets lost in that translation.
So is text is it too narrow of a container for that kind of visual complexity?
It absolutely is. I mean, text just lacks the expressivity for those really deep visual abstractions. Think about it for a second.
Right.
You can visualize rotating an object in your mind perfectly, right? But if you try to describe that process just using words, you lose all the critical spatial detail.
Right. And that loss is what created the need for a solution here.
Precisely. And that's where this new research comes in with something they call Latent Implicit Visual Reasoning, or LVR for short.
LIVR. Okay, so we're talking about giving the model a true visual thought that happens inside the model instead of just forcing it to talk about what it sees.
That's the whole mission. Previous approaches tried to solve this with what's called explicit supervision.
That's where we tried to like spoon feed the model helpful steps along the way, like drawing bounding boxes or something.
Exactly. First find the boxes, then predict this helper image. It was incredibly expensive. It was slow, and honestly, it just baked in all of our own human biases.
Because if you're training a model to solve a complex jigsaw puzzle, who's to say what the useful intermediate step even is?
You've hit the nail on the head. We might think in 5 steps, but the AI might need something totally different. Explicit supervision just fails where you need real abstraction.
So LIVR sidesteps that whole problem.
It does. It augments the LMM with KNU randomly initialized latent tokens.
You can think of them as like blank visual post-it notes, right?
Mm.
Giving the model extra space to scribble its own notes.
That's a great way of putting it. But here's where it gets really clever. It's how they force the model to use those post-it notes.
Okay.
They use this brilliant architectural trick. It's called visual bottlenecking. During the first stage of training, they modify the model's attention mask.
And what does that do?
It means that the prompt tokens and the eventual answer tokens, they are literally not allowed to look at the original image.
Wait a minute. You intentionally blind the prompt from the input. That sounds completely backward.
It is, and that's the genius of it.
So how does it know what to do at all?
By blinding the input, they force those latent tokens to become a bottleneck. They have to be the only channel carrying all the necessary visual information to answer the question.
Ah, so you're not telling it what to write on its little post-it notes. You're just creating a situation where it's forced to use them, and it has to figure out on its own what visual information is important enough to write down.
It discovers the optimal visual abstractions implicitly, just based on the final goal.
And the proof is in the performance, right?
Right.
This method, it's a task-agnostic enhancement.
And it consistently outperformed the old method, direct supervised fine-tuning, across 9 different perception-heavy tasks.
What were the gains like?
I mean, they were substantial, an average accuracy gain of over 6%. But where it really, really shone was on those abstract tasks.
Like the jigsaw puzzles.
Yeah, it saw a 12% jump there. And on something called functional correspondence, which is almost impossible for a human to label, it was up a massive 13%.
Wow, that is a huge leap, especially for a task like that.
It's a massive leap. It proves that AI is finding these internal visual shortcuts that we couldn't have even mapped out for it.
And when they looked under the hood, the visualizations confirmed it.
Yep. The latent tokens were learning to focus their attention on the critical evidence, whether it was the objects that needed counting or the specific parts of a machine for correspondence, all without being told to look there.
So it simplifies the whole process. You shift the focus away from expensive data annotation.
And you put it back on creating smarter architectural biases in the model itself.
So wrapping up, what does this all mean for you? LER is giving these LMMs powerful internal visual thoughts, that work better than anything we could explicitly design.
But because they're learned implicitly, they are, much less interpretable than plain text.
A bit of a black box.
Exactly. And that raises a really important final question for you to think about.
What's that?
If these abstract, implicitly learned visual representations work so much better than the steps a human would design, what might these optimal yet unseen ways of seeing the world eventually reveal about the nature of visual intelligence itself?